Out of the Coulomb blockade. So the way this works is that we have a left and a right electrode through which we measure the current with a bias applied containing a small particle in the middle. Now, to understand this, you need to know that the small particle acts like a little capacitor, and the energy required to put an electronic charge, so one electron on the capacitor, is given by E squared over 2c. If we divide this energy by the electronic charge E to get a voltage, this then is just E over 2c. The nano aspect comes in here because although E is very small, 1.6 times 10 to the minus 19 coulombs, the capacitance can be made very small if the particle is very small. For a spherical particle, C is 4 pi, the relative dielectric constant of free space, epsilon 0, times the radius of the particle. Now, epsilon 0 is 8.85 times 10 to the minus 12 farads per meter. So for a 1 nanometer particle, it turns out that delta V is about 0.7 volts. Now, if the spacing between these electrodes is such that the dielectric tunneling current is very small, so that an electron is required to tunnel from here to here and then from here to here, this process cannot happen unless the applied voltage exceeds 0.7 volts for a 1 nanometer particle. Why? Because the energy is not available to charge the particle. So if you were to look at a current voltage characteristic for this junction, you would see no current until the voltage exceeded 0.7 volts in either direction, and this blockading of current is called the Coulomb blockade. The device on the right here is the same as the device on the left, but an electrode has been placed very close to the sphere, separated by a small dielectric, so that by generating an electric field between, let's call this the source electrode, we'll call this the drain, between the source and the gate electrode, one can change the potential of the particle at a fixed drain source voltage. If you make the potential of the particle large enough, you can turn on the Coulomb blockade, in other words, make this 0.7 volts relative to the source, and then current will flow. This is the single electron transistor. The Coulomb blockade in real particles is actually a little more complicated. The reason for this is that our junction actually is not just a single isolated capacitance. There's a capacitance associated with the connection to the left electrode, the connection to the right electrode. There's a tunneling rate from the left electrode to the dot, and from the dot to the right electrode. Hanna and Tinkham have analyzed this in detail, and you see in these figures theoretical fits to tunneling through small particles measured in a scanning tunneling microscope. Most interestingly, single electron transistors can reveal some quite remarkable features in the Coulomb blockade. This is an example of a single electron transistor made from a columnar structure of semiconductor. So at the top is a pillar, a conducting pillar that corresponds to the drain, an insulating film of semiconductor, a very thin film of conductor for the dot, then another insulating film, and then a source electrode. A layer of insulation is applied to this structure, and then a gate electrode is evaporated on top of this. It's conventional in devices like this not to plot just an IV plot, because of course now we have three parameters: the gate source voltage, the drain source voltage, and of course the current that flows through the device. Rather than plot current, it's usual to plot the differential conductance, dI by dV drain source. And to do this on a three-dimensional plot of the sort shown in the slide. In order to understand this plot, you must realize that the dot has a series of allowed states on it for a charge trapped on the dot. In other words, this is the state energy, not just of the dot as an atom, but as an atom occupied by an electron, where the potential of the state is now raised by the Coulomb charging energy. So this device will then conduct if the drain Fermi energy aligns with one of these allowed states on the dot. And remember that these states can be swept up and down by the bias applied to the gate. So let's take a look at this so-called diamond pattern of differential conductance. It's plotted as a function of the gate source voltage on the vertical axis, the drain source voltage on the horizontal axis, so here is 0, and the darkness of the line corresponds to the value of differential conductance. So in regions where the current increases rapidly with drain source voltage, the line will be darker. So there is no current until you reach the Coulomb blockade energy at 0 gate source voltage, and so these points here correspond to the ends of these diamonds. However, if in a Coulomb blockade state you change the gate source voltage so as to sweep one of these states through the drain Fermi energy, then you will get an increase in conductance even at 0 bias, and that applies going the other way too, and that's the origin of these diamond-like structures. So at each point in the middle here, one state has swept through the drain Fermi energy. These points at the edge here correspond to the maximum value of Coulomb blockade. Note that the diamonds, the regions of suppressed conductance, are biggest for electron occupation numbers of 2, 6, and 12. This is because the dot forms the analog of an atom, and an atom has favoured closed shell numbers of electrons, and for this particular geometry, 2, 6, and 12 are the closed shells. Finally, notice this fine structure on the edges of the diamond. This comes from coupling to excited states of the dot, much like excited states of an atom.